Welcome to this exploration of the technology that revolutionized data storage. For over 50 years, hard disk drives ruled computing. Spinning magnetic platters stored everything from operating systems to family photos. Then, solid-state drives arrived, storage devices with no moving parts built entirely from semiconductor memory. SSDs didn't just improve storage, they transformed how we use computers. Boot times dropped from minutes to seconds. Laptops became truly portable. Data centers became feasible at scale. Let's understand how we got here. To appreciate SSDs, we need to understand what they replaced. The hard disk drive, invented at IBM in 1956, stored data on spinning magnetic platters. A read-write head floated nanometers above the surface, reading and writing data as the disk spun at thousands of RPM. This mechanical marvel served computing well for decades. Cheap to manufacture, high capacity, reliable enough for most uses. But mechanical systems have fundamental limits. Hard drives suffered from physics. Seek time. The head must physically move to find data. Random access is slow. Milliseconds that feel like eternities to a processor. Latency. Data isn't available until the disk rotates to the right position. Fragility. Spinning platters and flying heads don't survive drops well. Power consumption. Motors consume significant energy. Noise and heat. Moving parts generate both. By the 2000s, processors had become thousands of times faster than the 1980s. Storage hadn't kept pace. The hard drive was the bottleneck. Engineers had long imagined storage without moving parts. Solid-state storage uses semiconductor circuits to store data electronically. No motors, no spinning platters, no flying heads, just chips. The advantages were obvious. Near-instant access times, resistance to physical shock, lower power consumption, silent operation, compact form factors. The challenge was cost. For decades, semiconductor memory was far too expensive for bulk storage. Solid-state storage concepts predate hard drives. Magnetic core memory. Early computers used tiny magnetic rings wired together, fast but bulky and expensive. Read-only memory. Semiconductor ROM stored fixed data without moving parts. Used for firmware and boot code. EEPROM. Electrically erasable programmable ROM allowed rewriting, but slowly and with limited cycles. These technologies proved semiconductors could store data, but none offered the capacity, speed, and rewritability needed for general storage. The key innovation came from Toshiba in 1984. Fujio Masuoka, a Toshiba engineer, invented flash memory, a type of EEPROM that could be erased in large blocks rather than byte by byte. Flash memory used floating gate transistors. Electrons trapped on an insulated gate represented stored data. The trapped charge persisted without power, making the storage non-volatile. Masuoka's invention offered fast write speeds, reasonable density, non-volatile storage, no moving parts. Flash wasn't immediately practical for hard drive replacement, but it was a foundation. Fujio Masuoka's contribution is often underappreciated. Working at Toshiba, he developed both NOR flash and NAND flash. He reportedly did much of the work in his spare time without official support. NOR flash offered fast random reads, good for code execution. NAND flash offered higher density and faster writes, better for data storage. Masuoka later sued Toshiba for inadequate compensation for his inventions. He received a settlement, but his innovations generated billions for the flash memory industry. The first SSDs predated flash memory. 1978, storage tech developed RAM-based SSDs for IBM mainframes. Extremely fast but volatile, data lost on power failure. 1991, SanDisk shipped a 20-megabyte flash-based SSD for $1,000. $50 per megabyte, impractical for consumers. 1995, M-Systems introduced flash SSDs for military and aerospace applications where reliability mattered more than cost. These early drives proved the concept but remained niche products for specialized applications. Flash memory needed to get cheaper. Moore's law helped. As manufacturing processes improved, flash cell sizes shrank, capacity per chip increased, cost per gigabyte dropped exponentially. By the mid-2000s, flash memory had reached consumer price points for small devices, USB drives, MP3 players, digital cameras. The question became, could flash scale up to replace hard drives entirely? 2006-2008 marked the turning point. 2006, Samsung announced a 32GB SSD for laptops. Expensive, but a statement of intent. 2007, the OLPC project specified flash storage, betting on solid state for durability in developing nations. 2008, Apple introduced the MacBook Air with an optional SSD. Intel launched its X25M SSD, widely considered the first consumer SSD worth buying. The Intel X25M demonstrated that SSDs could outperform hard drives dramatically. 250 megabytes per second read speeds, 0.1 milliseconds access time, shock-resistant, silent. Making SSDs practical required solving hard problems. Write amplification. NAND flash must erase entire blocks before rewriting. A small update could require rewriting large amounts of data. Wear leveling. Flash cells wear out after thousands of write cycles. Controllers must spread writes evenly to prevent premature failure. Garbage collection. Managing deleted data and free space efficiently without impacting performance. Controller design. The SSD controller became as important as the flash chips, managing all these complexities transparently. Companies like SandForce, Marvell, and Samsung developed sophisticated controllers that made consumer SSDs viable. Flash memory prices fell relentlessly. 2008. 3.1 per gigabyte, 2012. 0.80 per gigabyte, 2016. 0.25 per gigabyte, 2020. 0.10 per gigabyte, 2024, and 0.05 per gigabyte. This 60 times price reduction over 15 years mirrors the pattern of other semiconductor technologies. Each generation of manufacturing brought smaller cells, higher density, and lower costs. 3D NAND technology, stacking flash cells vertically, accelerated capacity growth without requiring smaller cell sizes. SSDs evolved beyond hard drive replacements. 2.5-inch SATA drop-in replacement for laptop hard drives. Easy adoption but limited by the SATA interface. MESATA and M.2. Smaller form factors for ultrabooks and tablets. M.2 became the standard for modern laptops. NVMe over PCIe. Direct connection to the CPU's PCIe bus, bypassing the SATA bottleneck. Speeds exceeding 7,000 megabytes per second became possible. U2 and enterprise forms. High-capacity drives for servers and data centers. The evolution from SATA to NVMe was as significant as the move from HDD to SSD, unlocking performance that SATA couldn't deliver. SSDs transformed the user experience. Boot times. Windows startup dropped from 60-plus seconds to under 10. Application launches. Programs opened instantly instead of bouncing for seconds. Laptop durability. No spinning parts meant drops didn't destroy data. Battery life. Lower power consumption extended mobile computing. Silence. No more hard drive clicking and whirring. For many users, upgrading to an SSD felt like getting a new computer. Enterprise adoption transformed cloud computing. Database performance, random I/O operations went from painful to trivial. Virtualization. Many virtual machines could share storage without I/O contention. Search and analytics. Fast storage enabled real-time queries over massive data sets. Flash arrays. All flash storage systems replaced spinning disk arrays. Companies like Pure Storage, Violin Memory, and established vendors like EMC and NetApp built businesses around enterprise SSDs. Cloud providers, AWS, Google, Azure, standardized on SSDs for most workloads. Many contributed to the SSD revolution. Fujio Masuoka invented flash memory. Eli Harari, pioneer in flash storage commercialization. Intel drove consumer SSD adoption with the X25M series. Samsung became the dominant manufacturer of both flash chips and complete SSDs. SandForce developed influential controller technology. Jim Handy, industry analyst who tracked and explained the flash memory market for decades. Hard drives haven't disappeared, but their role has shrunk. 2010, HDDs dominated laptops, desktops, and most servers. 2015, SSDs standard in premium laptops, HDDs for budget and capacity. 2020, SSDs standard in most laptops, HDDs primarily for mass storage. 2024, HDDs relegated to bulk storage, archival, and cost-sensitive applications. Western Digital and Seagate, once dominant, have pivoted toward enterprise and archival markets where capacity trumps speed. SSD evolution continues. QLC NAND. 4 bits per cell increases density but reduces endurance, suitable for read-heavy workloads. PCI 5.0 and beyond. Even faster interfaces. 14 plus gigabytes per second possible. Computational storage, processing data directly on the SSD, reducing data movement. Storage class memory. Technologies like Intel Optane blur the line between memory and storage. ZNS, new interface allowing better optimization for flash characteristics. SSDs still face challenges. Endurance, flash cells wear out. Enterprise workloads require careful management. Data retention, stored data can degrade over time, especially at high temperatures. Cost at scale. For massive cold storage, HDDs still win on cost per terabyte. Environmental concerns, flash manufacturing is resource intensive. But for most computing tasks, SSDs have won decisively. Consider what SSDs have changed. User experience. Computing feels responsive in a way HDD systems never achieved. Software design. Applications can assume fast storage, enabling new architectures. Mobile devices. Smartphones and tablets were only possible with solid-state storage. AI and analytics. Fast storage enables processing that was impractical with HDDs. Reliability. No head crashes, no motor failures, just semiconductor reliability. The solid-state drive represents one of computing's most significant transitions. For 50 years, we accepted that storage meant spinning disks and mechanical limitations. Then flash memory, invented almost as a side project at Toshiba, matured into a technology that could replace hard drives entirely. The pioneers who developed flash memory, designed controllers, and drove manufacturing scale didn't just improve storage. They removed a fundamental bottleneck that had constrained computing for decades. When your computer boots in seconds, when your phone stores thousands of photos, when cloud services respond instantly, you're experiencing the solid-state revolution. The spinning disk served us well, but storage without moving parts is simply better, and we're never going back.